Hello guys, welcome to the what. So today we will see MATLAB simulations on DC to DC buck boost converter, and we will see its closed loop operation. Right. So we have seen its open loop non-isolating topology earlier. So in this video we will see its closed loop circuit. Right. So let's get started. So we all know that a buck boost converter is a DC to DC converter which will step up and step down the voltage according to the duty cycle, right? So if the duty cycle is given from 0% to 50%, it will step down the voltage. And if we exceeds the duty cycle by 50% till 100%, so then it will step up the voltage. So we have already seen the exact simulation, how to do open loop simulation in our earlier videos. So please do check that video first and come back here later, right? So today we will design a feedback loop for our circuit. So what is a feedback? So a feedback is something that we are sensing from the output, then we are manipulating it, then we are feeding it in the triggering circuit, right? And that triggering circuit, according to the value of this triggering circuit, it will trigger our MOSFET or IGBT in the main circuit, and our circuit will work, right? So if we see, these four portions will be same as our open loop, only this feedback loop is one addition, right? So let's see that how we can design a feedback circuit. So these are the components that we normally require to design a triggering circuit as well as our main circuit. And these are the components that we need to design our feedback loop or feedback circuit, right? A PID controller, it is the most important controller, and an add block, which is required to compare our reference to the sensed output, and a constant which is required to give the reference. So let's get started. Let's take one PID controller. Let's take one add block. Let's take one constant. So this is a feedback. So just turn these. Right. So here what we have, this is our constant, means we can represent this as our duty cycle. So at 25% duty cycle or 0.25 absolute value, we will get a step down voltage across this resistor, right? So just delete this. We will connect this PID controller here. Let's open this PID controller. Let's see the values. We will only use P and I, right, in continuous time domain from parallel, and the value of proportional will be 0.0001, and value of integral would be 0.1. So these are designed values. We can't use any random value. We need to tune our PID controller. Tuning means we need to decide the value of proportional constant, that is Kp, as well as integral constant, that is Ki. And if we are using a derivative, then we need to derive the value of this derivative constant, that is Kd. But right now we don't have to use this. I will make separate video how to for how to tune this PID controller, right? Right now just take these two values, that is 0.0001 as proportional constant Kp and 0.1 as integral constant Ki, right? Now just connect this add block here. Reference would be in the positive. Open this add block. We need to have one positive and one negative. So reference would be in the positive port and the negative would be the output. This one, right? So that's it. We just need to design this particular thing. So now we know that this amplitude is 100. So in a buck boost converter, we can control a voltage right from 0 till the double value of the given voltage. So if we have 100, so we can control from 0 to 200, right, the output voltage. So let's check. So let's start with the basics. So we already know that at 50% duty cycle, we will get the same output as the input in a buck boost converter, right? So our input is 100. So let's write here 100 for the reference. So now what this circuit will do, once we'll start this circuit, then the triggering circuit will sense our reference. The reference is 100. So it will trigger our MOSFET accordingly that the output should be 100 only, right? Let's play this, run this. So here we can see we are getting almost equal to 90, right? So if we open this scope, we will see that this will be 100 if we run this for a longer period of time. Let's do for 0.5. So we can see that it is coming around 99.87. So here we can see that the red line, the yellow line is our constant input voltage and the blue line is our output voltage. So we are getting 100 output. So let's check the gate pulses. So if we zoom in the gate pulses, we will see that we are getting a perfect 50% duty cycle, right? This blue line is the output of PID controller. So it will be up to 0.5, it is 50%. Let's see that as well. Here we can see it is around 0.5068. It is between 0.5068 and 0.507. So it is near to 0.5, right? So let's see that how we can change output. So let's put 150 here. So now I want 150 volts as an output. I'm not changing the input. We will change the input later. We'll see that what will happen then. So let's start our simulation. So here we can see we are getting 149.8, that is near to 150. We will not get exactly 150 due to the value of this capacitor, due to the value of this inductor, and due to the internal resistance of this switch, right? So we have these three losses, so we will not get 150. So here we can see that the yellow one is the input and the blue one is the output, which we are getting constant after a few cycles, right? So let's zoom in the pulses. Here we can see we have triangular pulses which are on an average 150, right? And let's see the output of PID controller. So now we can see the PID controller will trigger at around 0.61, right? So it is around 61%. So if we see the gate pulses, it will be greater than 50%, right? So it is around 61%. So this is a boost converter. Now this will work as a boost converter because the duty ratio is greater. The output is greater, that is 150, the input is 100. Now let's see what will happen if we put the output as 60. Right, so we can see that our output is 50, so we are getting around 49.97. If we compare, then we can see that 100 is our input and this blue line is our output. Right, we will get similar pulses. Right, and if we see the output of this PID controller, we can see that now PID controller will work around at 0.35, and the output that we will get, the duty ratio is smaller. Let's see, let's check the exact value. So we are getting around 0.338 and 0.3385, that is around 33.8% duty cycle. Right, now we can use this DC to DC buck boost converter in two places. One is an electric vehicle where we need to control a motor. So in that case, the motor is running through a battery. So we know that the output voltage of a battery is constant, right? So for constant output voltage, if we need to change or to control the speed of a DC shunt motor, it is better to use a DC separately excited motor. And we are tuning the DC shunt motor in such a way that it will behave like a DC separately excited motor. So if we want to control the speed of that DC separately excited motor by having a constant input supply, then we just need to change the triggering pulses, right? So let's run this simulation for a longer period of time and then try to change the speed, or let's try to change the output voltage while the circuit is running. So let's start from 100 only. So let's play. So now we can see we are getting around 100 volts in the output. Let's open the scope. So we will see here that we are getting 100 volts as an output and the circuit is still running. So now we will not close the circuit. We will change this 100 to 150. If we apply, then we can see here our output automatically changes to 150. If we see the graph, we can see here the yellow line, that is the input, will remain constant, but the blue line, that is the output, will increase and it will go to 150. Right, it can go to a precise value as well. So let's say if you are writing 127, for example, if we click OK, you can see here it will go to a precise value as well, near to 127. You open this, we will get a precise value, and to prove that this is precise, let's see this. So here we can see it is 127, right? It will not be a constant value, it will be in some triangular form, right? See, but it is a precise value. The area of the triangle above 127 and below 127 is equal. We can say that it is a DC value, right? So this is this is working in a boost topology. Let's try to change this in a buck topology. Let's put a precise value of 67.5. Right. So here we can see that we are getting 67.5 here, right? So that means it is stepping down the voltage. Let's see the graph. So we are getting some voltage here. Let's see the precision value. So we can see it is juggling around 67.5, right? With a triangular wave. Right? See, and we can see the yellow line, that is our constant input voltage, is already constant. This is our output voltage. So this thing, we can use this thing when we are using this topology or this DC buck converter in an electric vehicle. Now let's say we are using this thing in a solar panel, right? So in solar panel, let's understand how this will work in a solar panel. So in a solar panel, what we basically need, we need sunlight, which is not constant throughout the day, right? So intensity will change accordingly according to the time. So at morning 8 o'clock, the intensity will be different in compared to noon 12 o'clock, right? But the output of the solar voltage should be constant because we are normally charging the battery with it if it is off grid, right? If it is on grid, then we are synchronizing it to the grid using an inverter, but we will not go there. Let's assume that the panel is off grid, so we'll charge a battery. So for charging a battery, we required a constant output voltage from the solar panel. But this is not possible, right? Because the intensity of sun is variable throughout the day. So for that reason, we are using the same thing, but we will not change the output. We will change the means we will not change the reference, that is the like what we are getting from output and what we need. We will put this to 120 volts fix, and now from here we will change the output, that is the DC voltage. Sorry, we will change the input, so it will act as a variable sunlight, right? We want 120 volts to charge our battery. So let's play this. So we can see here we are getting 120 volts as an output. Let's check the scope. So in the scope, we are seeing that 120 is the output and 100 is the input. Now let's change the input. So let's change this to 80. Let's apply. So now the input is 80 volts, right? But we can still see here that the output is 120 volts. If we open this, then what we will get? We will see that that we are getting a constant output voltage, that is 120, the blue line, and the yellow line is the input voltage, which is now converted to 80. So what is this? What is this dip? So we can see here, what is this dip? So this dip is due to the PID controller value. So if instantly this input voltage is decreased, then PID controller will be unstable for a few milliseconds, and then it will be stable accordingly, right? So right now we are getting a constant output of 120 volts our input is 80. Now let's change the input to some other value. Let's say we are changing the input to 150 volts, high intensity sunlight, right? So now also we can see that the output is constant only, that is 120 volts. Let's see the scope. So here in the scope we can see that our input, that is the yellow line, will increase from 80 to 150. So according to it, this PID controller will get unstable for a few microseconds, and then it will be stable to 120 volts, right? So here we can see that our output is remaining constant if our input will change, right? So this is the closed loop simulations of DC to DC buck boost converter for electrical vehicle application as well as solar applications, right? So now if you have any doubts or if you have any questions, please do let me know. I'll try to get back to you. And if you want any other controller or converter to be simulated on MATLAB, please do let me know, right? Thank you. Bye bye.